All right, so today for our colloquium speaker, we have Ania Jayich, visiting from UC Santa Barbara. So Ania actually was an undergrad here, so welcome back. She got her PhD at Harvard and then moved on to postdoc with Jack Harris at Yale, and as I said, now is at UCSB and has been for several years. She's won many awards. I'll just name a couple. So the NSF Career Award, Air Force Young Investigator, and the PCASE Award as well. And after the discussion from last week, clearly early enough to be in previous administration. So anyway, without further ado, I guess I'll invite her to tell you about nitrogen vacancy centers and diamonds.
Thank you for having me here. It's definitely always a pleasure to come back. It doesn't happen frequently enough, but nostalgia runs high when I come back to Stanford. So today I'm going to be telling you about work going on in my group at UC Santa Barbara. And before I get too much into details, just to acknowledge the people who have done a large fraction of the work. In fact, Sophia is actually no longer in my group. She's in the audience. She's a grad student here. So this group of people really on a daily basis experiments with single quantum systems and probes quantum mechanical phenomena in a relatively straightforward and seamless way. And I think it's sort of instructive or to me sort of interesting to read what Schrodinger, one of the fathers of quantum mechanics, wrote, a little over 50 years ago, that in thinking about quantum systems, that we never experiment with just one electron or atom or small molecule. In thought experiments, we sometimes assume that we do, but this invariably entails ridiculous consequences. We're not experimenting with single particles any more than we can raise Ichthyosaur in the zoo, which were marine dinosaurs that died out of the world 59 years ago. So this was clearly outlandish to be dealing with single quantum systems. And I think this is really a testament to sort of experimental prowess over the last 30, 40 years in which we have enabled, we have now the capability of addressing single quantum excitations in a coherent way in a variety of systems. And this variety of systems not meant to be all-encompassing at all, but that includes trapped ions, where here's an image from Chris Monroe's group in Maryland, where each of these bright spots is an individual ion. And not only can they read out the individual ions, they have full, complete control over the quantum states of these ions. Superinducting qubits is another quantum system that exhibits quantum coherent phenomena. Again, one of the, I guess, most promising technologies for realizing quantum computers, quantum simulators, even single atoms, so moving away from sort of trapped ions and trapped atoms to atoms that are naturally trapped on the surface. This done down the road in the IBM group relatively recently, where the coherence of individual atoms could be probed. And on a much larger scale, nanomechanical resonators consisting of billions of atoms, that motion, the motion of that resonator can also be observed in quantum state, in a quantum superposition, for instance. Another example is that obviously done here. This one also is really pioneered by Oscar Painter and a lot of the work done by Amir Safafi-Naini, who continues that type of work, and also here at Stanford, the pioneer work of Yelena Vukovic, showing that sort of individual quantum dots in the semiconductor, in semiconductor nanostructures can also exhibit quantum coherent phenomena. Okay, so we've come quite far in our experimental control of these systems. Another such system that has recently attracted a lot of attention, I think for good reason, is that of the Nitrogen Vacancy Center in Diamond. This is a atomic scale defect in diamond that is being actively explored in various applications, for instance, for quantum sensing, even for quantum computing, for probing of condensed matter systems, something I'll show you today. And for a few reasons, just broadly speaking, the Nitrogen Vacancy Center in Diamond exhibits remarkable quantum properties in a very uniquely accessible way. At room temperature, in ambient conditions, in air, these emit light that allows us to detect them, light that's almost visible by the eye, that can be read out with a simple confocal off-the-shelf microscope. And furthermore, these little quantum systems, they can be, they're very small. They're almost atomic scale, like 2 atoms of nitrogen and vacancy. And because they're so small, and because they're very sensitive to their field environment, they make very good quantum sensors. Their small size allows them to be used as very high spatial resolution sensors of a wide variety of fields. And that's something that I'm going to talk more about today. And that sensitivity is sort of encompassed in this cartoon here, just to say that NV sensors are sensitive to magnetic fields, they're sensitive to temperature, to electric fields, and to strain. And also to stress and strain, yes. And also to fluctuations in these fields. And so it's a very versatile sensor, which I hope that in today's talk I convey that to you, that they have a huge amount of versatility in the variety of different fields, in the temperature, in the temporal scales with which they can sense these fields. It also comes with a downside that I'll also introduce and discuss at the end of my talk, the fact that they're sensitive to target fields that you want to sense. They're also sensitive to other sources of an unwanted sources of which end up being noise, and I'll talk some about that too, and how that can affect the coherence in ways that we've come up with to mitigate. So just as a brief overview of sort of work in my group, not all of which I'll talk about today, but one thing I will talk about is the fact that we've engineered these nanoscale, atomic scale sensors to reside at the apex of an AFM tip, so that they can become a versatile probe of a variety of condensed matter phenomena to probe magnetic textures on the nanoscale, and I'll talk about that. Something I'm not going to talk about is our work that employs nitrogen vacancy centers that are sandwiched or formed inside photonic and phononic resonators, but I won't talk about that. But at the end, I will talk about this very important issue of this double-edged sword of sensitivity, where the NV sensors are sensitive to fields, but again, sensitive to unwanted fields, that in particular are exacerbated near interfaces, which tend to be prevalent, especially when you're trying to do high spatial resolution sensing. And so I'll talk some about that as well. So now, taking a step back to be a bit more complete in my introduction of what the NV center is, it is a defect in diamond in which a single carbon atom has been replaced by nitrogen, and nearby there's a vacancy. These can be formed a variety of ways. They occur naturally if you just dig a diamond up with the earth. You'll probably find some of these. They can occur via implantation. One can implant nitrogen ions to generate those nitrogen substitutional defects, and in that process you also generate vacancies. One can also grow these defect centers into diamond, something that we actually do. I won't talk so much about that, but that's another way one can use chemical vapor deposition growth to grow diamond with these defects inside. So these defects have some pretty attractive properties, as I mentioned: optical readout, high spin, coherence. And so let me tell you sort of briefly how that emerges. So this NV center can be modeled sort of simply as having a ground electronic state and an excited electronic state separated by about a 637 nanometer photon. So this optical transition is useful both in initializing the state and in reading out the state. And there's also an associated electronic spin. So if I look at this ground electronic state, it's in fact a spin triplet. There's 2 electrons sitting around. The nitrogen has 1 electron beyond the carbon, and then it's grabbed another electron from the lattice, presumably from another nearby nitrogen atom. So this is a negatively charged NV center. There's 2 electrons, and as I said, those can form a singlet or a triplet. The ground state is a triplet, and this triplet levels are shown here, the ms equals 0, plus and minus 1 state. And these are very important, these levels, because these form, we can choose any of these 2 levels to form our 2-level spin system. Okay, so that's the spin that's going to be obviously sensitive to magnetic fields. Turns out that's also sensitive to other fields as well. And importantly, with these optical transitions, one can initialize the spin into the 0 state by just simply shining green light onto the NV center, and one can read out the spin state because this state turns out to be brighter than either of those two states. Now, I've mentioned that a lot of our work is directed at quantum sensing, sensing fields, and so let me tell you sort of a bit about how that can work. So if I now just look at this ground electronic state, again, it's a spin triplet, where even in the absence of a magnetic field, there's a crystal field that splits the 0 from the plus and minus 1 state. That happens to be at 3 gigahertz. That's a very convenient frequency, another nice aspect of the NV center. And again, this 0 state is brighter. It luminesces more brightly under green excitation than the plus and minus 1 states. Now, so I can use that fact to effectively form spectroscopy of this splitting by simultaneously shining a green laser and sweeping the frequency of some applied microwaves and monitoring the fluorescence. And what I see in this optically detected magnetic resonance curve is that I see fluorescence of 100,000 photons per second or so. And then when my microwaves are in resonance with this transition, I see a dip in the fluorescence as my microwaves drive transitions between the 0 and 1 state and cause the NV center to spend some of its time in a darker state. Okay? Now, that's in the absence of a magnetic field. If you apply a magnetic field or trying to sense a magnetic field through the Zeeman effect, that splits the minus and plus 1 angular momentum projections by an amount that's very quantitative. That's important, right? As a sensor, by an amount just given by G mu B, this 5.6 megahertz per Gauss. And again, if we perform one of these optically detected magnetic resonance curves, then that's a new one. But then we can, we see in this curve, we see two dips that correspond to the 0 to minus 1 and 0 to plus 1 transition. The splitting between those is directly relatable to the magnetic field, again, in a very quantitative way. The magnetic field along the axis of the NV center. So that's sort of, in a nutshell, in a simplistic way, how sensing works. One might ask, okay, I've said this is a quantum sensor. What makes it a quantum sensor? What limits the sensitivity, or what sets the sensitivity, the ability to detect small changes in the magnetic field, is really limited by the alignment of those dips in that magnetic resonance spectrum. So if I were to say, what is the DC magnetic field sensitivity, which I'm defining as the minimum detectable magnetic field that I can measure in, say, a 1 second measurement. You want this number to be small, right? You want to have smaller magnetic fields that you can detect. That is proportional to the inverse of T2 star, which is the quantum coherence time of the NV center, as well as to the gyromagnetic ratio, and then some other number here that sort of describes obviously how many photons I'm getting out and what the difference in contrast between the 0 and the 1 state is. But importantly, this T2 star is what's relevant to the sensitivity. And one can see that here also sort of intuitively, right? If I'm trying to measure a shift in the magnetic field, that's going to shift my peak over a little bit, and my ability to discriminate small shifts is going to be limited by the sharpness of these lines, and the sharpness of these lines is exactly 1 over T2 star, the quantum coherence time. Okay, so something I'm not going to talk about today, but something that's obviously is possible in the future, and really an ongoing direction, my lab and others, is to go even beyond this kind of, I guess, superposition type of quantum, to talk about the possibility of entangling multiple NV centers to gain even more enhancements in sensitivity. But that's still something that is not been demonstrated yet with NV centers. So, you know, what's all the excitement about quantum sensors? One can do pretty well with classical sensors. So just kind of thinking, what can quantum sensors give you? In what realms would you prefer to use a quantum sensor than some other type of sensor? Well, in this case, there's a couple of things that I think the NV center in particular offers. And these include spatial resolution. Again, because the NV center is a single spin, it's addressable on the single spin level, our spatial resolution is really limited by how close we can bring our spin to the sample in your study. And it turns out that we can do that, as I'll show you later in this talk, that we can place our spins within several nanometers of our target sample that doesn't have, that comes with a set of problems, which I'll also talk about, but there is, spatial resolution is a big allure of the NV center as a sensor. Sensitivity, the sensitivity, as I've already mentioned, is increased with this long quantum coherence time. The NV center has a particularly long quantum coherence time, even at room temperature, on the order of milliseconds, which is relatively long, especially for a solid state system. And also afforded by our high fidelity quantum state readout. Another reason these sensors are advantageous is they're very quantitative. As I mentioned, we can relate the splitting in this spectra to the magnetic field via known constants. Okay, so it's a very quantitative measurement, and it's very non-invasive. We're using a single spin as a sensor. Right? Your single spin exhibits very minimal back action on a system under study, as opposed to, say, bringing in some big magnet that might disturb the system under study. And lastly, the NV center in particular, maybe not the case for every quantum sensor, but they're very robust and easy to use over a wide range of temperatures, even up to several hundred degrees Celsius, in fact. In the broader scheme of, speaking of just magnetic sensors, I think it's also nice to see, where does the NV center sit? You don't want to use the NV center for every type of magnetic sensing experiment. Really, where you want to use the NV center is when you're interested in high spatial resolution. And so that's shown on this plot, where I plotted detection volume and sensitivity for, again, not a comprehensive list, but for several types of sensors that exist. And if you see here that NV centers do very well in detection volume, again, because of their small size and the ability to bring them very close to samples. And again, they have the added benefit of variable temperature operation, being minimally invasive. So what might one want to do with such a very small sensor? One of the holy grails of the field is really getting to nanoscale magnetic resonance imaging. Right? So as you know, when one gets an MRI of your brain, for instance, there are pickup coils that are picking up the magnetic field produced by processing proton spins in your brain. However, the magnetic field produced by those nuclear spins is quite small, and hence one needs many nuclear spins in order to get a large enough signal to noise, to be able to see a signal, and that's usually on the order of this many nuclear spins per voxel volume pixel, which limits the best conventional MRI microscopy to about 3 microns. If one could increase that spatial resolution or reduce the number of nuclear spins needed to see a signal, one can dream about being actually able to image directly the structure of a protein by imaging or detecting the magnetic field produced by each of the individual nuclear spins on that protein processing. So this is obviously a difficult challenge, but I think not crazy, and in fact, the whole field of using NV centers has made some good progress in that direction, in the direction of really single nuclear spin sensitivity with atomic scale spatial resolution to be able to reach this type of lofty goal. Just as an indication of some progress that has been made using NV centers as high spatial resolution magnetic sensors, by depositing proteins on the surface of a diamond with NV centers right below the surface, several groups have been able to detect the presence of single proteins. So much improvement over this 3 micron or 10 to the 12th, 10 to the 18th nuclear spins conventional MRI. Again, this example is just to highlight the sort of robustness of NV centers and their capability to be able to integrate with biological environments. For instance, some nice work recently has used NV centers to detect the magnetic field associated with propagating action potentials in a neuron. Okay, so those action potentials are current effective, which produces a magnetic field, a very small magnetic field, but it's possible to actually detect those in live neurons, wet solution, and all that. On the condensed matter side of things, something I'll talk a bit more about, There's also been nice work showing that one can use NV centers inside of these type of diamond cantilevers to, in this case, image, for instance, these helical cycloidal spin patterns in this case in a bismuth ferrite, which is a magnetoelectric material with some canted antiferromagnetism, which is being imaged here to really be able to probe local magnetization. And this idea of imaging condensed matter systems is something that's near and dear to my heart, something that I've been doing for a large part of my life, and just to motivate that being able to locally image a material system has a lot of advantages and has a lot of benefit that one would not be able to realize in a simple transport measurement alone oftentimes. So these are just a few examples of work not done using NV centers, but just examples meant to remind ourselves why imaging condensed matter systems is a useful exercise, and obviously here at Stanford, there's many people who subscribe to that philosophy. But here's an example of this case, a scanning squid thermometry measurement of a graphene washer. And what one sees here is that one sees these local hotspots it sees the temperature go up, which is an indication of in an area of location of enhanced electron photon coupling. Again, and being able to map these out is something that you would never be able to see if you just did a transport measurement. Slap one lead on one side, measure the current coming through the other side. It would be an average over the sort of physics going on in between your leads, where here you can really resolve those individual ones. Here's another example from Ziyak Shen's lab here, where they use a microwave impedance microscope to image these local conductivity, enhancements in conductivity in this pyrochloroiridate, and what these little local conducting regions are suspected to be conducting domain walls. Again, this type of information we would not be able to extract in a transport measurement alone. So for the NV Center, some types of systems that we're interested in imaging and are imaging, and I'll talk mostly about this work here today, but just an example of the sort of versatility of the NV Center of what one can imagine using it for. This sample could be, for instance, a sample containing magnetic skyrmions, which have nanoscale magnetic textures. I'll talk a bit more about that. One can also imagine imaging electron current flow patterns in the device, right? So if electrons move through a device, they produce magnetic fields. And by imaging those magnetic fields, one can back out what the type of current flow patterns are. And that could be interesting, for instance, in revealing the difference between, say, ohmic or hydrodynamic electron flow in a material such as graphene. This is a theory prediction relatively recently that predicts that in the ohmic flow regime, one expects to have sort of flow lines that might look like these white lines, whereas in the viscous sort of hydrodynamic regime, one might expect to have these types of honey-like flow patterns. This is something that we're actually working on. I'm not going to talk about it so much because, or at all, I guess. Those results are not quite wrapped up yet. But one can also image protein structures I've already alluded to, either by imaging directly the nuclear spins, which is admittedly quite hard, or by labeling a protein with electronic spin labels, which carry a larger magnetic field, and one can put those spin labels at precise positions on a protein and begin to infer the structure. This is something that we are, in fact, working on in the lab. Again, I won't talk about that so much today. But this is the type of system that we've built, the scanning probe magnetometer. So I will just have a few quick slides with some of the sort of the nuts and bolts of how it works. First of all, we had to make these diamond probes. I'll spend 2 slides on this. A lot less than the actual students' time spent making these types of structures. So short story is fabricating single crystal diamond is not straightforward. There's a reason why diamonds are very robust and good material. It's not easily etched by much. But what we do is we make an array of hundreds and hundreds of these diamond single crystal cantilevers. And at the end of the cantilever, we etch a little pillar, which is going to be our tip, which is going to house That's a zoom in of this little pillar, and we engineer there to be a single NV center that resides within 5, 10, 20 nanometers of the surface. The data that I'll show you today, the NVs were about 20 nanometers away from the surface. And we can pick the pillars that have one single NV per pillar to really maximize their spatial resolution. And then confocally, one can take a laser, scan it over, a green laser, scan it over this cantilever, monitor fluorescence as a function of laser position, and see that if you're collecting the fluorescence, one sees a very bright spot right here, which corresponds to the fluorescence of a single NV center. Actually, it's another nice benefit of these pillars, in addition to being able to position our NV centers close to the sample under study. They also help waveguide the light for enhanced collection efficiency into our collection optics, and so you can see we get on the order of 10 to the 5th photons per second. And then we've integrated this scanning probe magnetometer into a cryogenic system, and this just shows a zoom in of our home-built tuning fork cantilever system with a diamond probe hanging off the end. You can see here the RF for driving the transitions of the spin. We have a microwave waveguide, and this just shows our diamond pillar, in this case I think over a graphene sample, where this is our microwave antenna, our what we call an omega antenna. Okay, so this just shows you sort of what our system looks like. A few years ago, our first successful demonstration of using the NV center as a probe of nanoscale magnetism in condensed matter systems at cryogenic temperatures was imaging vortices in an iron thick-dyed superconductor. And here, what you see here is an image of these vortices taken at 6 Kelvin. And here really the main point was this is sort of a technological achievement that showed that we can extend previously shown NV magnetometry to cryogenic temperatures that I think opens up the possibility of studying a wide range of material systems. It's a bit ironic actually, because the NV center, as I've mentioned, is really nice because it operates at room temperature and air at high temperature, and it's really simple to use, and now we've kind of made our lives hard again by going to low temperatures. But again, that's where a lot of the, at least for condensed matter, where a lot of the interesting science is. Okay. So I'll tell you about, I guess, two imaging experiments that we've performed recently with our NV scanning probe magnetometer. In the first one, applying it to the study of skyrmions, which are magnetic topological defects that where in materials that exhibit certain types of magnetic interactions, one can realize these type of spin textures that look like this, where these show the spins. These can be on the order of nanometers to several hundreds of nanometers in size. These have attracted a lot of attention particularly in the engineering and sort of spintronics community, because they can be very small. They're topologically protected, and hence they can be very robust. And they're actually fairly easy to move. So when one thinks about sort of spin logic devices, one can move these bits with much lower power density than typical domain wall, say, memories. So here just shows an artist's conception of having a skyrmion being a single bit and moving it, say, between to a contact, and between, for instance, contacts, and driving it with currents. Okay, so these are very interesting. They're small, they're robust, they're easy to move. However, if one wants to really understand their interaction with pinning sites, the interaction with driving fields, their interaction with each other, one needs to understand their internal spin structure, which, given their small size, is quite difficult to do with a variety of other techniques. We have collaborated with Kang Wang's group at UCLA, who grew a thin film sandwich of materials, in this case this structure, in which one can realize the necessary magnetic interactions to realize skyrmions. In particular, one needs some inversion symmetry breaking in order for what's called the Bleszynski interaction to be non-zero. This is an antisymmetric exchange interaction that can happen in bulk crystals with broken inversion symmetry. And effectively, this Bleszynski interaction sort of favors a non-collinear alignment of nearby spins. So, exchange interactions can favor a sort of a ferromagnetic or antiferromagnetic alignment, and the Bleszynski will favor this sort of antisymmetric alignment. That inversion symmetry breaking can be engineered at the interface, which is what these guys are really good at engineering. And so they grew this sample on their own. They were able to take MOC, magneto-optical Kerr effect, microscope images. And what they're doing here is they're effectively generating skyrmions. They call it blowing skyrmion bubbles, but they generate skyrmions, and they can image these skyrmions. And you can see that their spatial resolution is, of course, limited by the optical diffraction limit of their MOC. And so we worked with them to image the internal spin structure with higher spatial resolution. And here shows one image, an NV image that we've taken of a single skyrmion in these devices. And one of the questions we wanted to ask ourselves is, what is this internal spin structure of the skyrmion? And there's I guess there's a continuous range of types of skyrmions, but one can think of, when you remember domain walls, you can have block type domain walls or nail type domain walls, where at the domain wall, do the spins, in this case, do they point azimuthally, or in this case, do the spins point radially as you cross the domain? So the spins, do they flip like this, or do they kind of flip like this? Okay, and one expects these different types of domain walls to depend on the strength of the DMI compared to the exchange interaction. So for increasing DMI strength, one expects these nail skyrmions, and whether one has a nail skyrmion or a block skyrmion drastically affects the way that it interacts with driving fields, for instance. And again, you can sort of have anything in between. Using our NV imaging technique, we were able to infer what's called the helicity angle, and to actually image that angle of the skyrmion for these particular structures. So that was something neat that we could do. Then we took an image, actually first we did this, if we take an image of a large area, in this case this scale bar is about a micron, and so let me just say one comment about how this image was taken. If I go back here, this image, you see the color scale here is the field magnitude, so we're at each point in the scan, we're taking a full ESR sweep to sort of map the splitting to get the full magnetic field. One can do that, but one can go a little bit more quickly by taking what's called a contour image, which is what I show here. So just really briefly, how that's taken is we fix the frequency of our applied microwaves to one value, and we monitor the fluorescence of the NV as we move the tip around, and it experiences different magnetic fields. And if it so happens that the local magnetic field brings the NV splitting into resonance with our microwaves, we see a dip in fluorescence, and we'll see a dark line. And then, but if the magnetic field does not match the RF frequency, then we see bright fluorescence. And we've arranged, in this case, we've arranged the magnetic field such that these dark lines, so these dark lines are effectively contours of magnetic field, and in this case, they actually outline the exact position of the domain wall of that skyrmion. Okay, so at the domain wall, that's the field that we're resonantly tuned to. So these sort of odd-looking structures map the domain wall of the skyrmion. So clearly, the most obvious thing here is that they're not round like that the cartoonish pictures are. Again, this is an indication of there being local inhomogeneities in the sample. Moreover, if we zoom in on one of these skyrmions, we see this domain wall. And if you look closely, you can actually see that there's a domain wall here, but there's also a faint outline of another domain wall here. And so what's happening is this domain wall is actually jumping in real time between these two stable positions, presumably between two pinning sites. We can see that by fixing our NV center in one location and taking one of these ESR curves, or ODMR, optically detected magnetic resonance curves, where you would expect naively just to see two peaks corresponding to one magnetic field splitting. But because the domain wall is spending some time in one spot and some time in another spot, we actually see two different fields during the time scale of the measurement, and so we see two discrete splittings. And as we increase the magnetic field, the domain wall, it's not shown here, but the domain wall sort of collapses and not collapses, but it settles on the smaller diameter position. Okay. So we know that it's jumping. Can we say something about the time scale? We know that we cannot see, in this case, we could not see the hopping happening in real time. So we sort of have a lower bound on the time scale of the dynamics. But can we say something about the faster dynamics, how fast it could possibly be? The answer is yes. And let me explain to you a little bit how we realized that we could do this. And this really relies on the fact that we're using this quantum sensor as our sensor. So let's just say we have an NV center and it's sitting next to a domain wall that can reside either in this position indicated by the red line or the blue. And then I were to say that the domain wall is jumping between these two spots with an average jumping rate chi. Okay. And so what the NV center is going to feel is it's going to feel a magnetic field that's high, maybe when the domain wall is close, it's low when the domain wall is far away, and again, this is jumping, exhibiting this telegraph noise with an average rate chi. So when the domain wall is in this location, the NV ODMR spectrum should look like this, where this corresponds to the magnetic field produced at the NV when the domain wall is there. And when the domain wall moves, then my ODMR spectrum will move. Good. Now this is what I expect to see, but only if that jumping rate, chi, is actually smaller, slower, than the splitting between these two. If the jumping rate is actually faster than that splitting, actually what you expect to see is you expect to see just one dip, because effectively you're seeing an average of the environment. This is very much exactly the effect of motional narrowing in NMR, which has been known, as most things in the NV community are discovered, has been known for over 50 years in the NMR community by these prominent guys. So the fact that we're seeing these the two dips in the ESR spectrum is, from that we're able to put an upper limit on the rate at which the domain wall is hopping back and forth of about 14 megahertz. And again, this 60 hertz, actually this is about 600 hertz, is the sort of time scale, the lower end of the time scale about how quickly we can actually measure. And just to say that this type of motional narrowing in a qubit sensor has been seen also before in a superconducting qubit in this experiment here. And recently we've actually, I think there's actually more creative ways than one can actually fill in this gap in terms of the time scale between 60 and 14 megahertz by using some other techniques from the electron spin resonance community, such as stimulated echoes and instantaneous diffusion. I won't go into that, but something that I'd be happy to talk about afterwards. Okay, so I mentioned, one of my theses here is that the NV is a very versatile sensor, and in addition to DC fields, it can sensor fluctuating fields. Another way that we can detect fluctuating fields is outlined here. So in sort of DC magnetic field sensing, effectively what one is sensing is some sort of phase evolution of a quantum state, a coherent phase evolution that's limited by the T2 star. But in another sensing modality, if one monitors the T1 time, the relaxation time of a two-level system, that relaxation time is sensitive to magnetic field fluctuations that have a frequency spectrum exactly at that splitting. And so that's what I'm trying to show here, is that if here I draw my NV, my three-level system, if this omega, I'll call that the relaxation rate, meaning if I were to polarize my spin system into this state, how long would it take for that two-level system, for the population to thermalize into some thermal mixture of, say, between the 0 and the -1 state? That rate omega is sensitive to the fluctuations at this frequency omega naught. So if one were to plot the sort of, let's say I have some noise power that the NV center feels, if I monitor the relaxation rate, this T1 time, effectively what that acts like is that acts like a filter function centered exactly on this frequency omega naught. So one can probe the noise spectrum of some material, and that could be interesting for a variety of systems to probe these magnetic fluctuations, because that could arise, for instance, from fluctuating single spins, from fluctuating currents, right? Again, currents produce magnetic fields, or from other magnetic systems such as spin waves or other materials near some transition temperature where spin fluctuations are often enhanced. So to demonstrate this, we actually did this type of relaxation T1 imaging to probe the fluctuating magnetic field produced by fluctuating currents to, in fact, image the conductivity of a material. So, as I mentioned, this relaxation rate omega is proportional to the noise power spectrum at that splitting between the 0 and the -1, which in our case is on the order of gigahertz. If I have a conductor, then electrons are moving around randomly back and forth exhibiting Brownian motion, and I can actually calculate quantitatively what the noise power spectrum of the magnetic field fluctuations is as a function of temperature, as a function of conductivity, as a function of separation of my NV center from this film, conducting film, and also the thickness of the film. Okay, so this is what we expect the magnetic noise power to be. And so in the experiment, what we did is we measured the T1. This is, again, in this case, our sensing, our signal. And when our NV is far away from the conductor, let's say it's really far up, we measure a T1, and that's the characteristic decay. So in this measurement, what I can do is I can polarize the NV center to the 0 state, which is a very non-thermally non-equilibrium state, and wait for some amount of time to see how long does it take to equilibrate some thermal population between the 0 and 1, where it gets darker over time, because that one state is darker. And the characteristic time scale of this decay is indeed the T1. Okay, so this is how we do the measurement. For an NV far from the diamond sample, far from the conducting sample, we get a T1 of about 5 milliseconds. This is typical for NV centers at room temperature. And then we bring the NV center nearby the conductor, and in this case it was silver film, and the T1 went down by a factor of a few. Then we could do this measurement at every point in a scan to image this local conductivity. So here we took a nano-patterned silver film, so this is an 80 nanometer thick silver film, and monitored the T1 of the NV center as we scan over this film, and we see that when we're over one of these conducting pads, the T1 goes down. When we're between the pads, the T1 goes up. So these conducting nanostructures locally reduce the NV T1. This is also quantitative. I already showed you this equation that relates the noise power spectrum density to the conductivity. And just to show you this quantitative nature of this imaging, what we did is we, as a function of height, we measured the T1 of an NV as a function of, say, distance to some metal film for 3 different metal films. As we bring the NV closer to the middle film, the relaxation rate increases. Fitting this curve to this functional form, which I already showed you, which is proportional to the conductivity, we can fit for the conductivity of the metal films, and indeed find for silver, aluminum, and titanium different values. These values are to be expected. They're somewhat consistent with what one would expect, a little bit lower than bulk conductivity, which is also expected given that these are thin films. So I think this is a really nice quantitative, non-invasive, and local nanoscale probe of local conductivity. In the future, I think this could be interesting, for instance, to probe, say, local conducting and insulating pockets in some, for instance, complex oxide that undergoes a metal insulator phase transition that might be non-uniform across a sample. And this is a lot of nice work done here in Ziyech Shen's lab in this realm. And so this is just a simulation of if we were to image, use this T1 imaging to image little metallic pockets inside of an insulator, using actually the types of contrast between conductivity you expect in some of these complex oxides. that we could detect these about 40, 50 nanometer size islands in a reasonable amount of time. Okay, so that's some work that we've done with imaging. Let me take a slight turn here to talk about this issue of quantum coherence at interfaces. For us, we're particularly interested in this because if we really want to reach this regime of really nanoscale or even sub-nanoscale spatial resolution, we need to bring our NV center very close to a sample. Let's say it's a target spin, a nuclear spin that we want to image. And so our dipole sensitivity, again, the number that we want small, the minimum number of dipoles we can detect in a 1 second measurement is going to go as r cubed over this e to the minus tau over t2, where t2 is the quantum coherence time. So we want to have really small separation and really long t2. But that's a challenge because anytime you come near a surface, things become a bit uncontrolled. The really protected diamond lattice is no longer there, and we have some uncontrolled surfaces. And that uncontrolled nature of the surface could come in the form of trapped electric charges, adsorbents, crystal strain, dangling bond spins. There's a myriad of uncontrolled elements, especially when we're working in air, that can happen. That can occur. And this is an issue for NV centers, not just for sensing, but also any type of experiments where one wants to couple the NV center's quantum degree of freedom to, say, a phonon or a photon, which often requires nanostructured devices, which necessitate surfaces nearby. And moreover, not just for NV centers, but for, I'd say, probably the main limitation to a lot of developing quantum systems is these interfaces. So for instance, in superconducting qubits, the interfaces between the superconductor and the oxide. For trapped ions, bringing trapped ions near to chip traps, which are one of the best ways to sort of make a scalable ion quantum computer. When one does that, one begins to see sort of anomalous heating at these surfaces. Even these optomechanical resonators that have been observed in their quantum ground state, their coherence time is suspected to be limited by the presence of individual amounts of small or discrete amounts of surface adsorbents. And nice work done here in Ken Muller's group several years ago, and in using scanning squids, saw the sort of density of paramagnetic spins that caused fluctuations in the squid readout. For NV centers in particular, several years ago we mapped this out pretty quantitatively in terms of measuring the quantum coherence time of the NV center, again, which is something we want to keep high, as a function of depth below the diamond surface. I guess for here, just focus on the green data points, which shows the Hahn echo T2 time measured for NV centers as a function of depth. And below, once you bring the NV center within about 20 nanometers of the surface, the coherence time starts to drop. So that makes it not a great sensor. Another thing that can happen with NV centers near surfaces, and I won't talk so much about this just to say that this is yet another surface-induced problem that can occur, is charge state conversion. So the NV minus that we love, that's the sensor, can give up an electron to surface traps or acceptor states or maybe local defects whose energy levels can be sort of affected by the presence of the surface. And generally, what we found is that in this recent paper that we sort of mapped out these charge state instabilities near the surface. Just a quick interlude to say that for starters, to be able to even, we're really interested in ultra clean materials. The surface is a bit harder to control, but we do start with very clean diamond by growing a diamond with a CVD process, and we engineer these NV centers to reside within nanometers of the surface using a delta doping technique. In a further effort to really maintain the coherence of these NV centers as best as possible in terms of the bulk material, we introduce vacancy so that this doping from the CVD growth is just introduced the nitrogen. One wants to introduce the vacancies as well in a very gentle process, and we do this with a transmission electron microscope to use the sort of lowest energy electron irradiation of about 150 keV, which just barely frees up a carbon atom. And we can also do this in a spatially localized way. But the point is that using this combination of CVD growth and electron irradiation, we can get consistently high T2s in the bulk. Okay, near surfaces though, actually I wasn't going to talk about that. In the surface though, things are less controlled. And what I want to show here is the NV center actually makes a very good spectrometer and probe of the origins of that surface noise, which affect the NV center, but also affect these other quantum systems. And so let me tell you a little bit how that works. As I've already mentioned to you, that relaxation can be induced between these two states by fluctuating magnetic fields at that frequency. But one can also get relaxation between these two states. But in this case, relaxation between those two states is dominated by electric field terms. Again, I have a delta m equals 2. The angular momentum changes by 2. So that's the first order, is magnetic dipole forbidden. So one can use the relaxation rates of this two-level system and this two-level system to be able to probe the nature of the decoherence spin bath, as well as the frequency spectrum. Right, so that's basically shown here, and we can also vary these splittings with a magnetic field to be able to kind of map out that frequency spectrum. And so we've done that recently, and here just shows the results, which basically show the we can map out both the electric and the magnetic noise components as a function of frequency. And I guess the upshot here is we find that electric field noise actually, sort of surprisingly, contributes strongly at frequencies less than 100 kilohertz, and given the dependence of the noise on the depth of the NV, we suspect that that's a dipole noise. So these are really efforts to try to understand on a more microscopic scale what is this origin of noise at these surfaces and how can we mitigate that. So one can take materials approaches, something that we're doing in the lab. One can also take approaches by controlling the NV center with various dynamical decoupling impulses, keep flipping the NV center every which way on the Bloch sphere to help rephase, recover the coherence of the NV center. But there's one more technique that I want to show you in the very last few slides of this talk, is a recent result that I think is also sort of fun. So as I mentioned, we see this magnetic noise contribution. We can estimate that there is some density of paramagnetic surface spins seen by us, seen also very similar densities intriguingly in Cam Muller's work with the scanning squids, as well as in the superconducting qubits. I still don't know what this is. I don't think anybody really knows what these noise sources are coming from. But there's a few neat things that I think we've discovered using our NV center as a probe of these spins. So in the presence of these electronic spins fluctuating, they're producing some magnetic field noise. Okay, we can actually turn the problem around. We can use the NV center to probe these spins and probe the frequency spectrum of these spins. And that's what we've done here using what's called double electron-electron resonance, where we use the NV center as an optical readout to probe the frequency spectrum and the dynamics of the surface spins, which this is a pretty powerful use of the NV center, by the way, because now we're able to sort of read out spins on the order of a handful of spins, which are nominally dark, and we're able to use the NV center as a window into their dynamics. What we see here is that these spins, this is a surface spin spectrum, sweeping the frequency of a driving microwave pulse on the surface spins. We see that these are G equals 2 spins. So at an applied field of 400 Gauss, we see the characteristic frequency dip that corresponds to these spin 1/2s at the surface. And they're really relatively narrow. So these surface spins have a pretty long quantum coherence time on their own, and they're sitting there in air at room temperature with really no control of the surface, which I think is frankly pretty amazing. We can even drive Rabi oscillations of these surface spins. Again, we don't even know what they are, but we can drive Rabi oscillations. So I think as a resource, actually as a sensor themselves, these electron spins, now I can bring the electron spins really close to my target system under study and just use the NV center as a readout of those. So I think that's an interesting direction. But let me tell you about, I was starting to introduce these because they reduce the coherence time of the NV center. How can we mitigate that? Again, one could try to get rid of them, but people have been trying for a long time unsuccessfully. And even if you did, it's probably going to show up after some time again anyways. So what you can do actually is very counterintuitively, you can start driving them. And so if I have these surface spins that are producing fluctuating fields, but now if I start driving them really fast, again, I can effectively motionally narrow their effect away. I can drive them so fast that their effect averages to 0, and that's what we've done, is we've measured the T2 of the NV center as we drive these surface spins, which is at a different frequency, and see that our T2, this is a plot of NV T2 without driving, and the red is with driving, and we did this for several NVs, and the T2 is always increased up to more than a factor of 2. And again, I think this is pretty powerful because I'm no longer doing any sort of typical dynamical decoupling on my NV spin. Right? I might want to use that NV spin. I still want to be able to do some quantum gates or some sensing sequences, and I don't want to use up the sort of bandwidth of that NV center with various dynamical decoupling sequences. I can just address the noisy environment on its own and effectively average that component away. And quantitatively, we measured the enhancement in the sensitivity of the NV center in the presence of driving the surface spins, and see that we get up to a factor of 5 enhancement in sensitivity. In particular, when we use the plus and minus 1 qubit as our sensor. And the reason that is, it's pretty simple to see. If I use this qubit basis, the minus 1 and plus 1 is doubly sensitive to magnetic fields. So that makes a great sensor, but it's also doubly sensitive to those fluctuating spins at the surface. But if I can remove the effect of those fluctuating spins, then I can have a sort of an overall higher enhancement in my sensitivity. So, as I mentioned, this is, I think, a fairly exciting direction, both in terms of a way to mitigate decoherence, but also these surface spins on their own, I think, are a very intriguing and interesting direction to go. This just shows that we can confirm that they really are at the surface if we measure this decoupled, the decoupled decoherence rate as a function of NV depth. We see that when the NVs get really closer, we can decouple more and more of the noise, indicating that they really are at the surface. Okay, so just to summarize, I hope I've shown you that the NV center is a versatile quantum probe that is giving us an eyes into condensed matter phenomena. Decoherence at interfaces is a major challenge, and I hope we're shedding some light on what's going on, and this is a path that we continue to move on. And one way of mitigating the effect of these paramagnetic spins of the surface is by driving them. And so with that, thank you. Just to advertise for anyone interested that we have some postdoctoral prize fellowships at UCSB from the California Nanosystems Institute Healing postdoctoral prize fellowships, as well as some soon-to-be-announced quantum foundry postdoctoral fellowships for a new NSF-funded center that focuses on creating ultra-coherent materials that exhibit quantum phenomena at UCSB. So, thank you very much.
Thanks for a great talk. Questions? Yeah.
Great talk. So one of the limits, as I see it, is the bandwidth of readout. You only get 10 to the 5 photons per second. What are some of the strategies you envision for improving that?
So there are a few. One I did not mention, but it was used in this simulation, and in fact, actually in this data as well. One thing one can do is, I guess it doesn't overcome the problem that you have a single spin and only emits so many photons per second, but you can do a lot better. So one of the problems with the NV center is when you do shine light on the NV center, you actually change the spin state. You can only shine light for a small amount of time, 300 nanoseconds per shot, before you start repolarizing the spin, and then you have to stop measuring and you have to redo your measurement. So that's to overcome that issue, one can actually do something called spin to charge, where you convert the spin state of the NV center to a charge state of the NV center, and then that is very stable for long periods of time, so you can enhance. In this case, we enhanced our sensitivity by a factor of 25 by doing that. So that's an example of techniques to enhance the or make the readout faster, I think still you're probably, because you have a single sensor, I think at some point there's a sort of I'm not sure if it's a fundamental issue, but that, you're only getting so much information out per second. So, one can go to more efficient detectors, right? So I think with something that people have started moving toward SNSPDs, that gives you a factor of some. You can structure your diamond to enhance the collection efficiency into your optics. You can have local, instead of having this big long optical path, like you can do on-chip detectors. So there's a variety of things that can really increase that are large, many of them are engineering challenges that can really increase your information gain rate. But in the end, it is still a single defect. I guess one other important thing is that at low temperatures, so one of the issues is not just the count rate, but it's also that the one state is only, or the zero state is only a little bit brighter, 30% brighter than the one state. But at low temperatures, you can do resonant excitation. And there, one state's completely dark and the other one's bright. So there are, all those techniques can kind of add up. And this is something that several people and we are working on. But again, you still have a single sensor, and you can only get so many photons out per second. So I don't think there's there's going to be a limit at some point.
Hi, sorry, you probably said it, but could you give me just like a rough idea of your scan rate and what it depends on, like how long it took to make?
I didn't say it, and that might have been intentional. No, so these type of scans, so T1 imaging is sort of particularly tedious because T1s are quite long. Okay, since then we've also come up with other ways to make that faster, but just to give an example, this type of scan took on the order of several hours. And I think it's using some of these techniques that I've just discussed, and even some of that we've already employed in our lab since this result. I think realistically one can get these types of images down to, say, tens of minutes probably. And I think, yes, okay. Maybe I'll just stop there. I can speculate about what one could do.
So to make one of these nice tips, does it live a long time? Is it?
Yes, that's another sort of nice thing about diamond is that I'm not going to say they're completely stable forever. It has happened that R&D centers over time, over 6 months or on that order, can spontaneously disappear. We don't understand what's happening. But there's no bleaching, for instance, and diamond being so hard, if we ever crash the tip, it's normally our sample that gets destroyed to the diamond. We've definitely, we have lots of...
Diamonds are not forever, right?
No. Yeah. No, in fact, diamond is in fact not stable at, in air. It's actually not stable. It's in a metastable state. But I'd say overall, these are very robust sensors. Generally over the time scale of an experiment, that is not an issue. The charge state instability, though, at surfaces does become an issue, but that's happening. That's something you just have to live with near the surface or improve it. But the actual presence of the Ania center being there is generally pretty long-lived compared to the time scale of most experiments.
All right, so I guess let's thank God one more time.